Let's begin with a classic puzzle about random walks, sometimes called a drunkard's walk. Picture this. We have a 100-meter bridge, and a man who is a bit tipsy starts standing on the 17th meter. At every step, he chooses randomly whether to move forward or backward by exactly 1 meter, each with equal probability, that is, 50%. We want to answer two key questions. First, what is the probability that he will reach the end of the bridge at meter 100 before falling off the start, which is meter 0? And second, how many steps on average will it take for him to reach either end of the bridge? Let's break this scenario down step by step. To clarify, we have a straight bridge represented by 101 positions in total, from position 0 at one end all the way up to position 100 at the other end. Our man starts at position 17. At each step, he randomly moves forward to position 18 or backward to 16, each with equal likelihood. His journey stops as soon as he reaches either 0 or 100. Think of those as the two possible ways to exit the problem. Our goal is to analyze the probability that he makes it all the way to the end at 100 versus falling off the start at 0. We also want to compute how many steps it will probably take him, on average, to hit either end. This scenario is a specific example of a random walk with two absorbing barriers, sometimes called a gambler's ruin problem. Absorbing barriers mean that once the man reaches either end of the bridge, position 0 or position 100, he stops moving. The process ends there. Being a symmetric random walk, at every step the man is equally likely to move forward or backward by 1 unit. Our job is to use mathematics of random walks to analyze both the chance he'll reach the far end and how long it might take on average. To formalize the problem, let's define n as the total length of the bridge, which is 100 meters. Our variable s is the initial starting position, which in this case is 17. We'll use capital P of s to represent the probability that, when starting at position s, the man will reach the end at 100 before he falls off the start at 0. Similarly, we'll use E of s for the expected number of steps he'll take before reaching either end. By setting up these variables, we can now use standard formulas from probability theory for random walks. For a symmetric one-dimensional random walk with absorbing barriers at position 0 and n, the probability that the walker starting from position s reaches the end at n before 0 is simply s divided by n in symbols, that's P of s, equals silver n. For our problem, that means P of 17 equals 17 divided by 100. This elegant result is a hallmark of symmetric random walk problems. Every step remains unbiased, so the winning probability depends entirely on your relative position between the two ends. Plugging our numbers into the formula, the probability that the man reaches meter 100 before falling off 0, starting at position 17, is 17 over 100. This gives us 0.17, or 17%. So, despite being closer to the starting edge, he actually has a 17% chance of making it all the way to the far side, and an 83% chance he'll exit at the beginning. For the expected number of steps, there is a straightforward formula for symmetric random walks with absorbing barriers. E of s equals s times, in parentheses, n minus s. This tells us the expected number of steps starting from position s until reaching either boundary. In our specific example, we substitute s with 17 and n with 100. So, the expected number of steps is 17 multiplied by 83. Let's complete the calculation. 17 times 83 is 1411. Therefore, on average, the man will take about 1411 steps before he either falls off the start of the bridge or makes it entirely to the other side. To interpret these results, notice that since the man starts much closer to 0 than to 100, the odds are heavily in favor of him exiting at 0. The probability of reaching 100 is only 17%, purely reflecting how far he is from each end. Meanwhile, the expected number of steps, 1411, is relatively high, because there is a lot of wiggle room between position 17 and the two ends. In symmetric random walks, Both probabilities and step expectations are tightly linked to your starting point's distance from each barrier, with the formulas following directly from this symmetry. To summarize, our answers are as follows. The probability that the man will make it all the way to the end of the bridge at meter 100 before falling off the start is 17%. The expected number of steps the man will take before reaching either edge is 1411. Both results come from simple, powerful formulas in random walk theory, applied to our specific setup. Thanks for joining me for this walkthrough of the classic drunk man random walk problem. If you found this video helpful and want to learn more interesting and useful math problems explained step by step, don't forget to subscribe to the channel. And check out datalooper.com, where you'll find tons more math and probability puzzles like this one, with clear solutions and explanations.